contemplative. It is almost hypnotic. It's like putting your hand on the third rail of the universe. If you play Go seriously, there is a chance that you will get exposed to this experience that is kind of like nothing else on the planet. Go is putting you in a place where you're always at the very farthest reaches of your capacity. There's a reason that people have been playing Go for thousands and thousands of years, right? It's not just that they want to understand Go, they want to understand what understanding is. And maybe that is truly what it means to be human.
When I was a kid, I loved playing games. I started off with board games like chess. Then I bought my first computer when I was 8 with winnings from a chess tournament. Ever since then, I felt that computers were this sort of magical device that could extend the power of your mind. Virtual environments and games. We think they're the perfect platform for developing and testing AI algorithms. Games are very convenient in that a lot of them have scores, so it's very easy to measure incremental progress. So I'm going to show you a few videos of the agent system, the AI. So let's start off with Breakout. So here you control the baton ball, and you're trying to break through this rainbow-colored ball. The agent system has to learn everything for itself, just from the raw pixels. It doesn't know what it's controlling, doesn't even know what the object of the game is. Now, at the beginning, after 100 games, you can see the agent is not very good. It's missing the ball most of the time, but it's starting to get the hang of the idea that the bat should go towards the ball. Now, after 300 games, it's about as good as any human can play this and pretty much gets the ball back every time. I thought, well, that's pretty cool, but we left the system playing for another 200 games. And it did this amazing thing. It found the optimal strategy was to dig a tunnel around the side and put the ball around the back of the wall. The researchers working on this, amazing AI developers, but they're not so good at Breakout. And they didn't know about that strategy. So they learned something from their own system, which is pretty funny and quite instructive, I think, about the potential for general AI. So for us, what's the next step now? Go is the most complex game pretty much ever devised by man. Beating a professional player at Go is a long-standing grand challenge of AI research.
All right, I hope you are pumped up to find out exactly what AlphaGo Zero has in store for you. And today I'll be giving you a brief introduction of the methods that are used in AlphaGo and AlphaGo Zero. And I hope you find this useful into thinking about how we can use this to solve other AI problems as well. So without further ado, this is AlphaGo. So I believe most of you have heard of AlphaGo, and AlphaGo played a historic match against Lee Sedol in 2016. And just now, that documentary that you saw earlier is the first 3 minutes of the AlphaGo movie documentary. I encourage you to watch the documentary. It's very well created. And it really highlights the struggles that Lee Sedol faced against the AI. And he actually won match 4 out of 5, which was pretty amazing. Okay, which means that the AlphaGo method is not fully trained yet. And that's where we have AlphaGo Zero. Okay, AlphaGo Zero and above has never lost to a human before. Okay, so this is something quite amazing and makes you wonder, wow, how is this going to impact the world? What can this do, right? So I hope I've excited everyone here. And now we shall be delving into the techniques that were employed into this ancient board game Go. And I will illustrate to you from the ground up what exactly goes into it. So let's move away from Go for a while and we move to a very classic problem that we always face in our lives. It's called the explore-exploit problem, or how to choose an optimal action. Okay, given many choices in your life, what school to go to, what food to eat, what shirt to wear, all these are your choices. How do you know what to choose? And if an AI can solve this problem of exploit, which is a fundamental problem in reinforcement learning, then essentially it can learn how to do things better. So let's bring the discussion back to our daily lives, okay? So imagine now you are going to have your dinner, okay? I hope you all have your dinner. So if you want to have your dinner right now, how are you going to choose? Okay, if let's say you like chicken, should I have Hainanese chicken rice or should I have Western chicken chop? So how do you decide this in your real life, right? Most of the time it just comes unconsciously, our minds just decide it. But maybe let me just illustrate to you like how this process might occur in our heads. So firstly, let me just say that we actually like both of them. We actually sort of tried both of them before, and we gave a score out of 5. We gave a score of 4 to the chicken rice and maybe a 2 to the chicken chop. Okay, I personally like chicken rice a lot, so I give it a higher score. Okay, so it may be just like one occasion that, oh, the chicken rice was really well prepared, but the chicken chop maybe bad mood, the owner didn't prepare that well. You know, maybe, okay, maybe the next time around I go and visit the store again, I feel like, okay, the last time chicken rice was not bad, I'll try again. Now I got a score of 5. Oh, not bad. Oh, then actually, right, if you continue this, maybe I will just keep exploiting the chicken rice. I keep eating the chicken rice again and again and again and again. Okay, because my average score here is higher than the average score on the right. Okay, so the exploit parameter has been very high in my head. So I really like the chicken rice. I keep going to eat the chicken rice. But what if one day, you know, the chicken chop change owner or some better ingredients used, and really the chicken chop actually is a rating of 5. Just that we just keep exploiting the chicken rice and we don't try out something new. Have you all had this experience in your life before? You just keep doing something you like, and then you never try out something different, okay, which might actually give you a better enjoyment. So maybe one day you decide that, okay, I haven't tried chicken chop for a long time, okay? I decide to explore it because I haven't tried it for a long time. I try it and then, oh, I got 5. It's like, oh, the chicken chop is not bad. Okay, so maybe the next time around you will have to decide between chicken rice and chicken chop, which one is better, which one should you do. So the moment you explore one time, actually, you actually decrease the parameter here a bit. So all this here has been like sort of decreased. Okay, so that whenever we try out something, we try to make the other choices more attractive. Okay, more attractive. So the moment you try out something, okay, the explore parameter tends to like decrease because it's like recency effect. Oh, I tried this recently. Okay, so AI is really, in reinforcement learning, it's really about this balance of explore and exploit. And yeah, if you all have this experience before, maybe you all can just give a thumbs up. Okay, just to let me see like any of you all have this dilemma before in your life, like choosing between 2 choices. Okay, so a fundamental AI problem really is about how to balance these 2. And this is actually also known in the literature as called the multi-bandit problem. Okay, so if you're interested, you can find out more. But the idea is similar. You try to exploit as much as possible, but you also give some avenue for you to explore other options so that you don't miss out on what could potentially be good. Okay, so now I move on to the next part. So the next thing I'm going to talk about is called Monte Carlo. So Monte Carlo is basically an algorithm, okay, that actually tries to simulate what could happen. Okay, it's about random simulations. So let me show you what it means, okay? All right, so y'all have heard of the game Blackjack? Okay, so if y'all have heard of the game Blackjack, you put a thumbs up, okay, over there. So what Blackjack tries to do is basically you need to try to hit as close as possible to 21, but you cannot overshoot 21, okay? Because the moment you overshoot, you lose the game. So suppose in this very, very simplistic kind of game, okay, the dealer, by right, the dealer's cards are closed. You only see like one of his cards, okay? In this case, we make it simple. We can see both of the dealer's cards, okay? And you have both your cards here. Should you hit or should you stake? Hit means you take another card, okay? Anyone can tell me based on your experience of Blackjack, will you want to take another card or will you not want to take another card? Okay, you can just put yes or no in the chat or like in your logo. Okay, thanks, Evan. Stake. Okay, so how are we going to find out what should the answer be, right? Okay, one way, and a way that a lot of machine learning algorithms use, is to simulate out based on probabilities, what all the possible potential cuts are, and then find the expected value. But in some cases, there's just too many things to simulate. There's too many probabilities because there's too many possibilities. Okay, the probabilities get very small and small. So in cases like this, in order to get like what could be the next action, you can use this method called Monte Carlo. Okay, and it is named because sometime back in the past, researchers use this method to gamble at casinos. Okay, they try to find out what is the optimal value for gambling games. And in case you're all wondering whether you should gamble, my answer is no, because it's all rigged in favor of the casino. Okay, just to let you know. So Monte Carlo, let's try to do Monte Carlo for the blackjack game. So we simulate random possibilities of the future. So I hit the card. I can get a 3, I can get a 2, I can get a 4, I can get a J. I denote my wins and loss, my wins as 1, my loss as -1, and my draw as 0. So you can see over here, 2 wins, 1 loss, 1 draw. That's about 1/4 average points. Okay. So then I also do the other possibility. I simulate the other possibility. I simulate a stake. And what happens when I stake? Oh, in this case, the outcome is kind of bad, right? I lose everything. So my average points is -1. So in this case, using the Monte Carlo simulation method, I sort of get an average value that hit is actually greater than stake. And so I should do the hit action. Okay, so I hope this illustrates to you how some random simulations can actually help you find out the value of a particular state. Okay, and this is used quite successfully in gambling games. Okay, poker, blackjack. I think mahjong a bit too difficult, but yeah, you get the gist of it. So Monte Carlo. And now we come to the crux of the algorithms that Go software has been using like over the last 20 years. It's called Monte Carlo Tree Search. Okay, so earlier on you saw the chicken rice and chicken chop. Okay, that's only one decision. What if you need to make subsequent decisions as well based on your first decision? So maybe I choose chicken chop first, then after that day 2 I choose chicken rice. So you have a tree of possibilities that will affect your future decisions as well. So if you need to do subsequent decisions, you cannot just do one explore exploit selection. You need to do multiple explore exploit selections down the tree. So we select the next state using explore exploit, and then at the end of it, if we want to approximate the value of that last state, then we use the Monte Carlo method that I described earlier, where we do random simulations to try to find out that value. So this is known as the Monte Carlo Tree Search algorithm. And let me just illustrate to you how this is done. Okay, so in the first phase of Monte Carlo Tree Search, you have a game tree. Okay, this game tree is like player 1 for the top, player 2 at the bottom, player 1 again, and player 2. Okay, basically it simulates out the possible board positions of your game. And then each of these arrows is a move that you can make, like square 1, square 2, square 3, and then this is like the board position. So how do we decide what move to take for each player, right? You can look ahead, player 1, look ahead, player 2. How do we choose what move is good? And again, this is where the explore exploit that I mentioned earlier comes in. We want to exploit as much as possible those good moves, but we also want to make sure that we have sufficient room to explore those possibilities that could potentially lead to better moves. So I have to balance my explore and exploit using some equation that balances both of them. So I choose here based on the explore exploit constraint. I choose again, then I reach all the way to the bottom node here. Okay, then the question is, if this is not the end state, what value? Okay, so after I reach the end node here, I do the expansion step, which is basically I take, again, using the explore exploit constraint, I choose another move to explore. Okay, so at this final board state here, what is my value here? Because if this is not the end state of the game, where like you win is a +1, you lose is a -1, draw is a 0. If this is somewhere in the middle, let's say it's a go board, and you play the game halfway, how do you tell what value of this board position it is? Okay, so I think I have given you all the answer on the next part. The answer is you simulate the game. You simulate a random game. Okay, you can simulate more than one actually. You can simulate as many as you want based on your compute power. Okay, and then at the end of it, you get your score here. It's either +1, -1, or 0. Okay, +1, -1, 0. So after we do a simulation here, okay, the average of these values of what we get for the games, okay, will then be my score here. So this will be the score for this. So I simulate all the way to the end of the game, and then based on that, I update this node here, this game state, saying that, okay, this is a win position or this is a lose position. Okay, and that's not all. Okay, after you get win or lose, you update the value here. So if this is a win, then this one will be updated 1, and then this will be a loss for the other player. So it's -1, 1, -1, and so on. So you can actually update the value of that game itself to the nodes above. And then after that, it will help to bias the decision later on in the next phase. When we come back again over here, armed with the new value of this new game, okay, we can actually have a different value for the exploit equation. So based on the outcome of the games that you have done, you can actually select a new and improved path on your next iteration. So if you were to keep doing this iteration again and again, you will explore more and more of the game tree, and then you will also be able to get more and more accurate values of the values of your states. Okay, so Monte Carlo Tree Search, if I were to summarize, okay, it spans a limited compute budget you have because compute power is limited. You can only explore so much. Okay, you think about this way. Okay, imagine you need to make a decision about chicken chop or chicken rice. Okay, if you were to explore all the possibilities, okay, I think you'll just be sitting down at the table and not choosing any meal to eat. You starve. Okay, there will be a limit to how long you have to think about it. So like a computer as well, there's a limit to how long they have to think about a decision. So you repeat this procedure as many times as you can afford your compute power for. Okay, and after that, what you do is basically you just choose the move that is most selected as your next move. Okay, this is Monte Carlo Tree Search, and used in Go programs, it has reached amateur done level. Okay, but it has never beaten a Go professional. In fact, this Monte Carlo Tree Search, when played against a Go professional, the Go professional can give it 9 stones handicap and it can still win. And the Go professional can still win. So this procedure is nice. It tries to limit the search into spaces that are most likely to win. However, the game of Go is just so complex. Okay, 19 by 19 board, 361 moves. Okay, and then every single move after that is like times 360 times 359 is 361 factorial possibilities. Okay, I hope I got the calculation right. 19 by 19 to be 361. Okay, so based on this, how are you going to filter your search such that you search more effectively? That's a difficult problem, isn't it? So Monte Carlo Tree Search offered a glimmer of hope, okay, for AI programs back then. Okay, but it was quite clear that this approach alone wasn't going to hit professional level. In fact, it was projected that based on this approach, perhaps only in the next decade. So in the next decade, probably about 2030 or late 2020s, then we can beat Go professionals using this kind of approach because it's just too complicated. Okay, so this is exactly what has been done for some games using a prioritized search like a Monte Carlo Tree Search, but it's not enough. Okay, these are the reasons. Okay, the rollouts may not be an accurate gauge of your value of that board position because there could be a sequence of 100 moves down the line that if you play perfectly, those 100 moves lead to your win. But because you are doing random search, you may not be able to search until that state. Okay, you may not get the right value of that state using Monte Carlo rollouts. So there's a huge limitation with Monte Carlo rollouts when you have too many possibilities to look into. Okay, and also you need to do lots of simulations in order to get the average value, to approximate the average value for a larger state space. And okay, that is the beauty of where I'm going to go next, the beauty of neural networks. Okay, I hope you are familiar or have heard of the term neural networks. It's basically this wave of AI. This wave of AI right now has been propelled by neural networks. In particular, they go by the name deep learning. So AlphaGo, neural networks combined with Monte Carlo Tree Search. Okay, it basically puts Monte Carlo Tree Search on steroids and gives it a flexibility to model, okay, what could happen with a neural network. Okay, so you don't have to search that much. You can actually search to a limited extent and then use the neural network to search the rest or to approximate a search. Okay, let me explain what I mean. Okay, for those who don't know what's a neural network, I've given you this slide here to roughly illustrate what it is. It is like this. You have an input, like a cat or a dog. Okay, then you go through a neural network to process that information. And then output could be like classes, like is this a cat or is this a dog? Okay, there are different kinds of neural networks, but the idea is like an input-output relationship. It tries to map the input, okay? It tries to map the input to the output And basically after mapping, okay, it actually learns this, what is this mapping function by itself, okay, using this thing called back propagation. So neural networks are very flexible. You give it the input, the output, it can sort of learn how to map it. It actually works very similar to like how the brain works. That's why they call it neural network. Although the similarities actually don't go very far. Okay, the similarities is probably only at the connection level. After that, after that, it doesn't really mimic the brain that well. But even so, it is very flexible. It's able to model a function. Okay. So in AlphaGo's case, what is my input? My input is the 19 by 19 baud state. Okay, I need to process this baud state, and then the program needs to tell me something. It needs to tell me what move to make, right? What move to play. Okay, so over here, instead of having only one network to tell you what move to play, AlphaGo uses two networks, one policy network and one value network. Okay, so how do you view this policy network and value network? A policy network basically tells you what move to play. It tells you how good the moves are. Okay, and then helps you to choose your move. The value network tells you based on that certain board position whether you will win or not. So there's two different things that they actually use. And why use these two, I'll explain later. But you just need to know that AlphaGo takes in the Go, the game of Go, the board state, and outputs two values, the policy value and the value. Okay, the policy network value and the value network value. So what neural network should we use to model this? Okay, for those who are familiar with the field, okay, this board state could be viewed like an image where each of these stones have a value like 0 or 1. If there's a stone there, you can do it for a black stone, a white stone, and for an empty board position. Okay, you can do it in terms of feature planes where we have like the different aspects of the board modeled in each 19 by 19 plane. And this, if you look at it, if you look at like red, green, blue feature planes, it sort of looks like an image, right? RGB, red, green, blue colors. That's how we process our images. You can have more channels, okay? And then we can just make all these channels together, and we can pass it through this neural network called the convolutional neural networks. Okay, I don't have time to go through what CNN is, but do Google it if you are interested. CNN helps to process images, okay, and is very effective at doing so. Most state-of-the-art methods right now use convolutional neural networks for images. And so this being the nature of the Go bot, it sorts of like, it intuitively wants us to use a way to like process images to do with it. Okay, it's also quite ingenious because if you think about it, you know, I actually played Go before AlphaGo won Lee Sedol. Yeah, I was thinking that Go is the last unconquered sport. I want to do well in it. Okay, so I trained quite hard in Go. Okay, I didn't reach professional, but I was playing on KGS, reached about 4Q. So I think Go, when you play, actually you look at the relations of the stones together, and then like it sort of forms some beautiful picture in your head, and then you can sort of like figure out where to put next based on that picture. So that's why when people say Go is beautiful, actually it's really like in the literal sense, like it looks beautiful, and there's some moves that really strike you as beautiful, some as ugly, you know, that kind of thing. So it really looks like you can use an image to do it, and that is probably why we have conquered the game of Go 10 years earlier. Okay, because if we process things differently as an image, we actually see more spatial relations, and we can sort of generalize more. Like one side of the board, top left can generalize to the bottom right. That's the nature of a CNN. Okay, so I move on to the next part. I will explain to you what each network does. Okay, so a policy network. Okay, a policy network, basically how I view it is it restricts the amount of possibilities you consider. It limits the scope of what you think of as a possible next move. Okay, it's like choosing the beautiful moves to focus on in your game of Go, or I mean in a game of whatever they use it for. You choose the next most plausible move that could lead to a win. And how is this trained? Okay, so this is actually trained. Okay, this is actually the AlphaGo Zero method of training it. But the way it's trained is using a Monte Carlo Tree Search. And then it just does the explore, exploit constraints that I did earlier. It explores the next few states, exploits the next few states, and then it basically chooses the next move. Normally what will happen is that the move that is selected the most number of times, it means it's the most is good. Okay, because it's selected the most number of times means you exploit more, right? If you exploit something more, like if you eat your chicken rice more than your chicken chop, it probably means your chicken rice is tastier than the chicken chop to you, right? I mean, you think about it. So what it means is that we can actually take these values and we can train a neural network given this bot state here. Okay, given this bot state here, what are the probabilities that I should play my next few moves? So to get probabilities, okay, I simply just like do the average across all moves like that. Yeah, so I can train the neural network to output the probabilities of what is a nice move to me. And so next time, I don't have to do my Monte Carlo Tree Search simulation. I can actually just, use this network here. And even without doing any simulation, I use my neural network, I can find out what are the nice moves. Can you see the beauty in it? We basically converted this Monte Carlo Tree Search into a neural network so that the neural network will just like, you don't even need to do a simulation, you just need to pass it through that neural network, the input-output relation, and you can get what moves actually can help you win better. That's beautiful. And then you can see the next step. You can then use your updated neural network here, and then you can get even more accurate simulation, and then you can update this simulation to be even more accurate in the neural network, and you can keep repeating this process again and again to get better and better AI. Yeah, you can see how it can link already. So I would say the crux of AlphaGo is really, it brings what you can do in a look ahead back to its current state, and then it gets more and more accurate right now. It can predict the future more and more accurately, and eventually it becomes superhuman. Okay, so next we have the value network. So what is the value network? Okay, the value network is basically, just now we talked about Monte Carlo Tree Search and the Monte Carlo rollout to determine the value of a state. What if we could get a value network to tell you the value without the rollouts at all? Then you stay going through like hundreds of moves. Imagine you're at the start of the Go game, you still have 200 moves left to go. If you need to simulate those 200 moves, that will take quite some time, right? You need to play the whole game to do it. What if the value network can already tell you what's the outcome of the game? So even without playing the whole game, I can already say that, okay, this move is a mistake, or this bot state, you will lose. Okay, amazing, right? You don't even need to play the game. You already know that at this state, you lose or you win. Okay, and actually, Google DeepMind researchers, they found out that this estimate is even more accurate than the Monte Carlo rollouts that they did. That's pretty amazing, because this means that Monte Carlo rollouts, if you do for huge state spaces, because of the number of possibilities that there could be, you may not get the right value. And somehow this value network just does it better. It's a very simple thing. You just take the game outcome, and then you update all these previous states of the game with the game outcome, and you keep doing it for all the games that you have. So value network helps to eliminate this aspect I call depth. Okay, basically it means that I can simulate to the end of the game. Sorry, is there some sound? Okay, I can simulate all the way to the end of the game, even without simulating. Can you see the beauty in that? I can simulate the end of the game. I can get the outcome for the end of the game even without simulation at all. All right. So now I move on to some infographics from the AlphaGo paper. So I just want to walk you through what AlphaGo did. Okay, just briefly, because my focus will be on AlphaGo Zero. Okay, so firstly, what they did at first is, you look at the left here, you have the human expert positions they took from like amateur games or semi-professional games. And then they can do a classification here. Basically, if you all played Go before, there's this thing called Zumego, or basically what is the next move. So really, given a board state, what is the next best move? What is the best move that the next player can make? Okay, so they actually just train this. Given the board state, what's the next best move? They train it as a classification problem, okay, using this supervised learning policy network. Okay, there's this rollout policy also. It's also doing the same thing. Given this board position, what's the next best move? Okay, but the rollout policy actually will be used, okay, in order to, the rollout policy will be used in order to actually predict, okay, what is my Monte Carlo rollout. Basically, it is used to select the moves for the rollout, so that you don't roll out every single random move. You roll out the moves that respect like good moves. So this is the rollout policy. Okay, for AlphaGo, they use half-half. They use a rollout policy halfway. They use a rollout policy for the value and a value network for the other half. Okay, in AlphaGo Zero, later you will realize that, this is no longer used in AlphaGo Zero. Okay, it's inferior to the value network. Okay, so now let's just focus on the policy network. So this policy network trained with human games, okay, human knowledge. Okay, the weights are then transferred to the reinforcement learning side. So the reinforcement learning says hi to the supervised learning method, say, thank you humans for giving me my introduction to Go. Okay, from here on, I don't need you anymore. I'm going to improve by myself. So this is the self-play part. So from a reinforcement learning policy network, it does the self-play. Okay, it updates the policy networks and the value networks, and it becomes even better. It does even more self-play games. It gets even better, and you repeat the cycle, and we get AlphaGo. Okay, and the two main networks that it uses, which I will go in detail in the AlphaGo Zero part, is the policy network and the value network. The policy network is used to choose what are the next good moves to focus on, while the value network gives you the evaluation of that move, of that bot state as well. So together, it eliminates the breadth of the game using the policy network by limiting good moves, not searching all the possible moves. And it eliminates the depth of the game because there's no need to do rollouts all the way to the end. I can just use my value network to give me an estimate. And this is very beautiful. It's even better than Deep Blue that beat Gary Kasparov. Okay, because Deep Blue uses some form of minimax, okay, which basically still searches through the entire state space. Okay, just that they use some clever heuristics to cut off. Okay, this essentially is like more or less the real deal. The neural network itself decides what are the good moves to focus on, and it decides itself what is the value of that move all the way to the end of the game, the breadth and the depth, the policy and the value network. Okay. All right, let's move on to the next part. So if you thought AlphaGo was impressive, then be prepared for AlphaGo Zero. Okay, AlphaGo Zero basically tells humans, like, actually, your knowledge may not be necessary. Why don't I just learn from scratch? And that's AlphaGo Zero. The zero over there means zero human knowledge. Okay, AlphaGo Zero just uses the Monte Carlo Tree Search method with the neural networks, and it just does reinforcement learning through self-play, and it beat AlphaGo. Okay, so if Lee Sedol managed to win game 4 out of 5, 1 game out of 5 against AlphaGo, I don't think he will win any game against AlphaGo Zero. He's much stronger than AlphaGo actually. Okay, although one thing is that they didn't really do a showcase match anymore after that. Okay, but based on their internal games, this is actually better. So quite surprising, right? Like we always thought human intuition was good, but the computer just told us that actually maybe human knowledge is flawed after all. Okay. So what is AlphaGo Zero roughly doing? So I lead you through the first part of the image. So first we have this thing called self-play. Okay, self-play is basically a way to generate data to train the neural network. And the self-play will be done through two networks, the student and the teacher network, which I will go through later. Okay, so in self-play, we play against each other. The AI play against each other, and they use like Monte Carlo Tree Search to determine what's the next move at each bot state. So after I determine the first move, I use Monte Carlo Tree Search, I determine the next move, and so on until the game ends. When the game ends, I get this value Z, which is basically the game outcome, +1 for win for player 1, -1 for loss for player 1, and 0 for draw. Okay. And then over here, what we do is we then do the neural network training. Oops. We do the neural network training. How do we train this? Okay, so what we want to do is we want to make the neural network more and more accurate at doing the prediction for both the policy network and the value network. So we train the policy network given the bot state. We pass it through some convolutional neural networks. Okay, over here they use this architecture called ResNets, 20-block ResNet, if you are familiar with it. If not, just stick to convolutional neural networks. Okay, so this basically goes through this entire stack, and then it generates the policy network and the value network. And what it does is that what we want to do is we want to make this policy network that's generated through the neural network, okay, to be as close as possible to what? To the target value, which is the Monte Carlo Tree Search probabilities. Okay, because when you do Monte Carlo Tree Search, you actually look ahead further. It's actually a more accurate estimate. So even without doing the search, I want to make my probabilities be as close as possible to as though I did my search. Can you see the beauty there? It is trying to look ahead more without even doing the look ahead. That's why I said earlier. So it's quite cool. You can just train your policy network like that. And then what do we do with the value network? How do we tell what is the value of the game? So the value of the game, what we do is we take the game outcome, which is Z, and then we just minimize the difference between V and Z at each state. So this is used mean squared error to train, okay? And basically it tries to minimize the prediction error of this value estimate at each bot state to match the actual game outcome. And that, with these two core mechanics, is AlphaGo Zero. I will now go through the Monte Carlo Tree Search part of AlphaGo Zero in detail. Okay, so you understand how Monte Carlo Tree Search is done. Okay, it's slightly different from how I described Monte Carlo Tree Search earlier, because now it incorporates neural networks. It's a Monte Carlo Tree Search on steroids. Okay, so first up, okay, just to let you see, we actually select a bot state all the way using the explore exploit constraints. And what do we use for exploit? Exploit is just the average value of the game state here, Q, which you can see in the third step is just the average value of the states that is below it, updated back here, Q. So we actually use the Q value over here, which tells us how good this move is. This arrow represents a move. Okay, and this is actually based on the average of the values below it. Okay, so this is how we exploit. Okay, the higher Q value means the move is better. So we actually want to exploit by selecting the highest Q move all the time, right? But then, as what we mentioned in the chicken rice, chicken chop example, you don't want to just keep eating the chicken rice. Maybe the chicken chop is nice, but then you just miss out. You went on the wrong day. You want to try something different. So you also need to explore. And then this is your explore. U is the explore mechanism. Okay, but we want to explore smartly. We don't want to just explore all other possibilities. Imagine if you have chicken rice, chicken chop, and 100 other stores. You don't want to just explore all the 100 stores, right? You will not enjoy yourself that much because you really like the chicken rice. You just want to explore a limited other of side dishes or limited number of choices of other stores to explore. And that's where the policy network comes in. Remember earlier, policy network helps you to choose which are the moves that are the most promising, the most beautiful. And so you bias your explore to actually choose those moves that look better to you. Choose those other stores you never explored before, but you choose those that seem better to you. Okay, you don't anyhow explore the other stores. So in layman terms, this is how AlphaGo Zero chooses its move. It exploits what is best, the Q value, but it also gives some value for exploration, which is the U value. Okay. All right, 3 more minutes. Okay, let me try to end soon. Okay, so over here, the Monte Carlo Tree Search here, the next part will be instead of random rollouts, we actually have a value network V, okay, that gives the state evaluation. So once we reach the end of the game, we choose a move. Okay, instead of doing the rollouts, we just use our value network and boom, we get our value. And then the last step, we just do the backup. Okay, then we just keep repeating this again and again and again and again, and we can get very, very accurate move selection probabilities, move selection tools using Monte Carlo Tree Search. And that is really, they only did this 1,600 times in AlphaGo Zero, and it's really very good. We can even beat AlphaGo already. So yeah, that's for your information. Okay, so I talk about self-play. So self-play is very important in this AlphaGo Zero architecture because you need to spar at the right level. So over here, I have the Hikaru no Go comic here. If you all read it, the main character Hikaru has a lifelong rival called Akira. Okay, and basically they both compete with each other. They want to like be better than each other. Okay, and it's very important to have a right teacher. Okay, because if let's say you spar against someone, if you are too good, actually you learn nothing because whatever you do, mistake or not, you still win. So you don't really learn from your games. If that person is too good and you're too lousy, you lose all the games. Then you also don't learn anything because everything you do doesn't make a difference. So you need to be able to win some, lose some, ideally 50-50. Okay, so we have a student network and the teacher network. Okay, initially around the same standard. Okay, and then the self-play games, okay, will only train the student network to update the policy and the value network better using the earlier method that I described. Once the student surpasses the teacher, like 55% or more win games, okay, the teacher then initializes to the student value, okay, which means the teacher becomes as good as the student. And then we repeat this cycle again and again to update our student so the student gets better and better. Okay, I'm going to end soon. Okay, this is my second last slide. Okay, so there's this other thing to take note of is that actually human features can be distracting. Because in AlphaGo, they use all these features over here for their planes. But in AlphaGo Zero, they only fed it the rules, okay, which is like the stone color and the player color. And everything else is learned by itself. You don't even need to do liberties, capture size, or this, not really required for the game. And you can see that using the reinforcement learning, the blue color curve, it actually predicts less move than using the supervised learning, which is using professional moves. Okay, it means that professional moves, if you use the professional data set, you predict better. I mean, understandable. But you might think that, oh, maybe supervised learning is better, right? Because it predicts professional moves better. But if you look at this other graph on the right, you see that the reinforcement learning within 24 hours, it already beats the supervised learning approach. Okay, and within 30 hours, it beats the AlphaGo Lee, okay, which is the AlphaGo that won against Lee Sedol. So you can see that AlphaGo Zero using just pure reinforcement learning, although it doesn't predict human moves very well, it sort of is quite good because it already surpasses the human players so fast within a day. Within a day you can surpass already, which also points out that maybe human moves can be flawed. We maybe don't have the capacity to think as far as a computer. So okay, this is my last slide. So how do we achieve superhuman performance? I summarized. Firstly, you need a clear objective. In Go, it is easy. You can either win or lose the game or draw. So you want to keep maximizing the winning objective. You need the basic rules of the environment. It should be clear, okay? It shouldn't be like imperfect information because if not, it'll be hard to actually simulate. So your basic rules of the environment should be there so that it can learn through self-play. And lastly, it needs to have a continual way to keep improving this objective, mainly through self-play and self-play at the right levels as well. Okay, and with that, I conclude the sharing of AlphaGo and AlphaGo Zero. And yeah, I would like to just open the floor for any questions. Oh yeah, do check out my blog if you're interested in more AI stuff, and my Twitch as well. It's over here.
Okay, thank you, Chong Ming. Yeah, so before I move on to share the questions that you all have sent to me privately, can I just check whether anyone would like to pose a question in the chat or just speak over the microphone? Okay, if not, feel free to post while I share the questions with Chong Ming. Okay, so I think there are three groups of questions that I can see over here. So let me just start with those that are directly relevant to the materials that you covered today. So the first question is that can current AI goes beyond games with clear objectives? So the example that is given over here is MMORPG games.
Ah, nice.
So if the rules changes, do you think the current AI will be able to perform at a current level that you have shared with us earlier?
Okay. So if it's MMORPG where the rules are not very clear because like the objective is not very clear, maybe the objective could be progress. If you could somehow model that progress inside your RPG, like a progress meter, like maybe Pokemon, how much progress you go to the gym, like 1%, 2%, 3%, you can actually feed that progress meter as your objective. Okay, but in this case, because AlphaGo is more like a two-player game, you self-play, so RPG will be a little different. Okay, for that you might have to use other methods like queue network, queue learning, where you try to like simulate the environment and then improve your assessment of the environment's value function. So actually you can do a single player AlphaZero, okay, but it's sort of similar to this thing called the deep queue network. Okay, in fact, they have combined deep queue networks and AlphaZero into in a paper called MuZero. If you're interested, let me just tell you what it is. MuZero. Okay, that can do for both single player and two-player games. Okay, but my experience with it is that it takes very long to train. You know, if AlphaGo takes like 3 months to train, MuZero will take you a year. Okay, so because it learns the rules of the environment on its own. Okay, but I would say that for RPG games, okay, people have tried doing like deep queue network on like Pokemon Red. Okay, it just doesn't work that well because in order to get that 1% progress, you might do like a series of like very defined steps. You need to ride to the gym, you need to pick up your Pokemon, you need to train it, you know, that kind of thing. It just it's too open world. You see, if there's a more constrained board like 19 by 19, okay, but Pokemon can go left, right, left, right, left, right. You can forever be in the same spot all the time. I mean, if you all play Pokemon before, you will understand. If there's this thing called Twitch Plays Pokemon last time, it took like a few months for it to complete the Pokemon through mass inputs. Yeah, so if the environment is not too constrained, okay, you need to have an objective that gets it closer and closer to that objective. If not, it will just be trapped. Okay, so especially for open world games, that's the main issue. And I'm glad you actually bring up RPGs because actually my next research, I'm actually trying to speedrun an RPG using some reinforcement learning techniques.
Yes, it's a great coincidence. Yeah, so let me move on to the next question. How can AlphaGo be applied in the real world context? So I think this participant is asking whether it can be applied in maybe industry or work setting instead of just games.
Okay, so it really depends on the work setting you are talking about. Okay, some settings are tougher, some are easier. If the work setting is in a perfect information, by perfect information, I mean you already know what's the outcome if you do a certain action. Like if I press this button, this lever will activate. If I press this button, this other lever will go down. If you already know that all these are for certain, okay, then you can actually learn through self-play. Okay, especially like if you have two robots trying to like play robot soccer or something, you can actually learn that through self-play. I mean, because all the stuff is already certain. Okay, but what if it's an uncertain environment, right? Actually, uncertain environments can also use an AlphaZero method to learn. Can, but let me tell you the caveat. Because if it's an uncertain environment, it is probabilistic. It means that my value estimate is no longer clear that it's always this value estimate. Because sometimes 50% is a value -1, 50% is a value 1. So what does this mean? I cannot just run one simulation. I need to run like hundreds of simulations, thousands of simulations to get the probabilities of these transitions right in order to get you the right expected value for that state itself. So it is possible to do for imperfect information, but I would say that it will just take a very, very long time to train, and it may not be practical for real world environments. In fact, a lot of things in real world environments that people want to develop right now, they build a simulator where everything is certain in that simulator. Self-driving cars, you simulate it. Okay, you have GTA, Grand Theft Auto, you know, they actually do quite realistic car scenes and stuff. You can use a simulation to train your car. Then you deploy it out in the real world. So people are doing this kind of things. You train in a simulation, train extensively, and deploy in the real world. Because reinforcement learning needs a lot of data. You need to train really, really extensively. Okay, I've done some experiments in it. I can vouch for the amount of data reinforcement learning is needed. That's why also my other research that I'm trying to do is trying to minimize the amount of data needed. Okay, it's really a lot of data. I mean, if you're in this field, AlphaGo Zero might be very impressive, but you know, before they did AlphaGo Zero, which ran in like a few days using 4 Google TPUs, AlphaGo ran in months using hundreds of GPUs. Okay, how are you going to do this in your real life data? AlphaGo using a Go board 19 by 19, such a constrained environment, months of GPUs. How do you train for an open world environment? So all these are very interesting research questions that have no answer right now. Okay, it is a difficult problem, but in order to achieve general AI, you need to solve all this. Okay.
Okay, thanks. Okay, so the next question I think is someone that is studying physics from the way the question is being asked. Yeah, so the question is that as the computing power continues to increase in the future, so with the emergence of quantum computing, does it mean that the current strategies that we are pursuing in computer science is no longer necessary? So I guess the question is asking whether everything can be solved using brute force if we have enough computing power.
Okay, so my answer is if you have enough computing power, yes. Okay, but how much is enough, right? Are you going to wait for the universe to explode before you get your answer? Okay, because like if let's say if the problem is unbounded, you need like infinite simulations. Okay, of course, if you can guarantee me you can get infinite simulations in a finite amount of time, consider it solved. You solve P equals to MP, you get a Nobel Prize in computer science. Okay, but unfortunately for current devices right now, we are bound by the finite compute power problem. Okay, if you can do infinite computations in finite time, sure, you maybe don't even need neural networks. You just do your Monte Carlo Tree Search, search every possibility. Okay, with the quantum compute coming up, okay, I'm not sure whether it's going to come anytime soon. It's quite difficult to stabilize your qubit. It needs to be in a very special environment, and it's very massive and bulky right now. But suppose one day we get quantum computing, then essentially we can solve a lot of problems that we have difficulty solving right now through brute force using quantum computing. And I would say that that would speed up the compute. But I would like to say that I believe any form of compute has its limitations. It cannot compute an infinite amount of things. So essentially, we'll still need to have smart techniques to like sort of approximate the future values. And I would say neural networks would still play a part even with quantum computing. Okay.
Yeah. Okay, thanks. So the other question is also about maybe the general AI scenario. The question is that is AlphaGo Zero a step towards sentient AI? So I think for this participant, he's referring to I think recently there's an article,
right?
yeah, and also
Okay.
about the recent Google engineer issues. Yeah.
All right.
So please share your view.
All right, don't be deceived when people say AI is sentient. Okay, it's far from it. It's still using probabilistic rules and like self-train to actually get the outcome. It's basically trying to pattern match and give you the most likely outcome. Okay, a sentient AI is quite far right now. Based on my understanding, I think we are still quite far from it. I mean, if we can solve an open-ended reinforcement learning problem first, then maybe we can think about how to build sentient AIs, because I believe like sentient AIs maybe you need to build on top of current deep learning. Like current deep learning maybe is layer 1. Maybe you need to do layer 2, layer 3, layer 4, maybe do until layer 10. Then you can start to think about a computer being sentient. Okay, right now we are still at baby steps. Okay, as much as you think that AI has progressed a lot, we are really still at baby steps compared to like the human brain. Okay, AlphaGo, yes, better than humans. Okay, but Go is not exactly the thing that computers are like have difficulties in. It's still mass compute. Okay, human brains don't do that compute very well, but human brains do generalization quite well. We can tell like a banana, a pear. AI takes a lot of examples to train. Humans just train with a little bit. Yeah, so I would like to say that if you want to think about sentient AIs, I think you don't have to worry for at least the next decade or so. Yeah, based on my estimation. Yeah.
Okay. Yeah. So I think I have one last question on my list. I think for this participant, he's interested to do a PhD. So he's asking, would you recommend doing a PhD and why so?
Okay, I'd like to ask PhD in what? In AI? I suppose AI, right?
It's not listed. Maybe just assume that it's a PhD in AI or ML in general.
Okay, so you have to ask yourself whether you like to find out new stuff, research stuff, or do you like to apply stuff? So you want to do applied AI, basically like you want to take the state-of-the-art models and apply it, like use a Hugging Face transformers and do your chatbot, sentiment analysis. Maybe you don't need a PhD because actually all these tools are open source, most of them, and you can just code it with some help from some online blogs and stuff. Okay, but if you want to find out more about like the inner workings of AI and how to like make it better, how to make it work for more situations, like how to make it run an RPG game maybe, yeah, you know, then consider research. But if your interest lies in just applying what has been done into some cool projects, then maybe you don't need your PhD. Okay, just bear in mind PhD is a very trialing moment because you are actually forced to come up with something new, and it may be quite uncomfortable, especially if you are very used to like the Singapore education system where you are being fed like what to study for. PhD is very different. PhD, you have to find out what you don't know, which is even tougher than studying what people have found out. Okay, so but I would say that my journey has been quite fun. I quite like what I'm doing. A lot of free time, okay, to explore what you want. And yeah, if you are interested in it, why not?
Okay. Yeah, thanks, Chong-Ming, for sharing with us your knowledge and your experiences today. Yeah, so can I check whether there's any questions before we end off today's session?
Okay, actually, I got some direct messages. Let me just
okay.
see.
Yeah, please.
Okay, so someone asked whether the YouTube link can be shared. I think Evan. So the initial video that I shared is called AlphaGo movie. Okay, just type it on YouTube. You should be able to see the documentary AlphaGo movie. Okay. Next, we have would adding from Ryan. Would adding studied geosekis where both sides have some clear immediate move make the Monte Carlo tree faster, since you can expect the opponent to make a common move in a specific situation? Okay, the answer for this is yes. Okay, because you can actually just ignore all the possible moves and just focus on one move. Okay, but the question is the Joseki correct? How are you sure the Joseki? Joseki is a common move, especially like common sequence. How are you sure that human studied Josekis are the best? Okay, so that's the question. So if you want AlphaGo to use Josekis, you'll be constraining its ability to find out new and exciting moves. Okay, so it will help with the elimination of the search depth, definitely, search breadth, because you already know what move to do next. But it also will mean that you are constraining the AI. Okay, yeah, thanks.
Okay, yeah, thanks, Chong-Ming, for sharing with us today. Yeah, thanks for motivating the AlphaGo example by using the chicken rice and chicken chop example, which we know is a very valuable and limiting commodity in Singapore for the last few days.
Oh yes, the chicken, right?
Yes. Okay, thanks everyone for joining us. We'll share with you once the video link is ready. Yeah. And thank you and have a nice evening in Singapore.
Okay, bye everyone. Have fun.
See you everyone.